All right, hello everybody. Welcome to the last regular lecture of the mini for Math Background for ML. So as you probably all already know, there's only one class left, which is the final exam on Wednesday. Today I figured I'd start out by doing an example that's related to what we were discussing last class, which is Lagrange multipliers for constrained optimization. So I figured, so we talked about, how to construct, how to use Lagrange multipliers to solve a constrained optimization problem. So I figured I'd go ahead and set up and solve a simple optimization problem using the Lagrange multipliers. So here's the optimization problem. We're going to minimize x minus 2 squared, half of that, plus half y minus 4 squared, subject to the constraint that x has to equal y. All right, so this is a pretty simple optimization problem, but it's actually kind of a useful one. So you could imagine that you're solving some giant regression problem, and half of your training examples are on one processor, where you would learn one vector of weights x, and half of your examples are on another processor, where you would learn a different vector of weights y. And in order to enable parallelization, what you would do is you would have one processor responsible for the second half of the objective, one processor responsible for the first half of the objective, and then a Lagrange multiplier that says they have to come to the same solution. Right? So here, this is not obviously a full regression problem. You've got one training example, 2, and you've got just one feature you're trying to learn, a constant. Here you've got one training example in the other half and one feature you're trying to learn, and so you just constrain this very simple regression problem to give you the same solution on both processors. So obviously we haven't talked about how you would go about setting up the communication between processors, but at a high level what you would do is the processors would send estimates of the Lagrange multiplier back and forth between each other. And that would be much less information than sending their entire data set, and so you would be able to have lower communication, enabling a faster parallel algorithm. Again, that's all at a very high level, just as sort of motivation why we would think about solving a problem like this. All right, so let's go about solving it. So the first thing we're going to do is we're going to add the Lagrange multiplier. So there's one constraint, this one, and we'll add a Lagrange multiplier for it. So we'll rewrite. We're going to minimize, and now we're going to specify we're minimizing over an x and y, just to be clear. And then our opposing player we'll call the Lagrange multiplier alpha. And we have 1/2 x minus 2 squared plus 1/2 y minus 4 squared, right? So that's just copied from the objective function of the original problem. And now we add the Lagrange multiplier, which is alpha times the constraint, right? So this constraint is equivalent to saying that x minus y is equal to 0. So we'll have alpha times x minus y. All right, and so alpha here is the Lagrange multiplier. And if you remember, the way that this works is suppose that the xy player plays x and y that are different, then x minus y is going to be non-zero. And that means that the alpha player can make alpha really, really large. And therefore make the whole thing be very positive, right? If x minus y is positive, then alpha will be large and positive. If x minus y is negative, then alpha will be large and negative. So that means that the x minus y player loses if x is not equal to y. And so the x and y player is gonna satisfy this constraint in order to do well in the game. All right, so this is how we're setting it up using Lagrange multipliers. Now, we talked about a whole bunch of algorithms for actually solving it. I guess the one we recommended was stochastic gradient descent. For this so for stochastic gradient descent, we just repeatedly select a term and take a step along its gradient simultaneously for the xy player and the alpha player. In this example, we can actually, we don't even have to go that complicated. We can just differentiate and set the derivative equal to 0 and solve it that way, right? And you know, as always, we would have to check and make sure that the solution we get actually corresponds to a solution, right? The same way when you solve a pure minimization problem, you have to check whether your solution corresponds to a local minimum, a global minimum, or, you know, saddle point. But here, actually, it turns out that there's only one solution, and it's going to be the global solution. So let's go ahead and do that. So we'll start, we'll call this objective L. It's a function of x, y, and alpha. And we'll write out dl is a function of dx, so that's equal to, for this term, x minus 2, and then there's an alpha x over here, so that's plus alpha dx, right? So this is the differential in terms of x. We can do the same thing. dl is equal to y minus 4 from this term, minus alpha from that term, dy, right? And then in terms of alpha, dl is equal to x minus y d alpha, right? So here I've just used the standard rules for differentials to go ahead and differentiate L with respect to x, y, and alpha, right? And so we differentiate and set to 0. And then what that tells us is that we have to just scroll that up to the top there and go to a fresh page. So in order for this expression always to be 0, the coefficient of dx has to be 0. So we have that x is equal to 2 minus alpha. Same thing for this guy. Y has to equal 4 plus alpha. And for this guy here, x has to equal y. And so this is a set of 3 linear equations and 3 variables. We can just solve it. In particular, let's say we take this second one and subtract the first. So that says that y minus x is equal to 4 minus 2 is 2. Alpha minus alpha is 2 alpha. And then y minus x is the same as 0. So that means that, right, divide by 2 and move the terms to opposite sides, you get alpha is equal to minus 1. All right. So here we've solved for alpha, and now we can plug in alpha equals minus 1. Here this gives us that x is 3, and then alpha is equal to minus 1. Here this gives us that y is equal to 3. And so just as a sanity check, we do satisfy the constraint that x equals y. We figured out this value of the Lagrange multiplier alpha, and that lets us figure out what the optimal values of x and y are. So that's that's how you would solve solve this simple problem. We've got a question on Piazza, which is how big should we let the Lagrange multiplier value be? So this is a question, I think, about, you recall, we were trying to interpret this, new objective that contains the Lagrange multiplier term, and I said that, for example, if x minus y is positive, we would let alpha be very large and positive, right? And the answer is it doesn't really matter how large we let alpha be, right? So as long as, like, you know, let's say x is 1 bigger than y, and we let alpha be 1 billion, right? Then this term effectively doesn't matter, right? The xy player is going to totally ignore this term and just be really, really, really unhappy about this term, right? And so the x minus y player is going to say, well, I better not set x equals y plus 1. Right, and then the same, right, because effectively the alpha player can make this objective be arbitrarily large in this case. If you wanted to say a specific value for alpha, it would be plus infinity, but that doesn't really make sense because you're only allowed to play real numbers. So I think it's probably more accurate to say that you just take alpha to be arbitrarily large and positive. Same thing if x minus y is negative, you would take alpha to be arbitrarily negative, right? Arbitrarily close to minus infinity. All right, so here we. So here we go. This is our solution. Right, we have this, this, and this, and so basically. This is just supposed to be a simple example of how you would work through using a Lagrange multiplier. If it's confusing, oh, okay. Here's another good question on the on Piazza. So somebody's asking, why didn't we bother doing SGD? Why did we just differentiate and set to 0? So in general, for a complicated problem, you wouldn't be able to, you'd get some equations by differentiating and setting to 0, but you wouldn't be able to solve those equations, right? They'd contain functions that were not analytically tractable. Here, because our problem is so simple, when we differentiate and set to 0, we get just a simple set of equations that we know how to solve. So I guess the answer is, after you differentiate and look at the result, if you can set to 0 and solve, that's what you would always do. But in most practical cases, the equations are going to be too complicated to solve that way, so you would have to run a minimization algorithm like SGD. You could also, there's plenty of other algorithms you could use instead, like Newton's method, for example, but SGD is the one that we've been using in class, and it's a fine choice for this, for this example. All right, so keep asking questions about the example, and I'm going to go now to our next topic, which is in fact our last topic for the semester, and that's discrete optimization. So, oh, okay. Oh, so somebody's asking about an alternate way of solving this, which is if we go back up here. Well, actually, let's write it on in a fresh line. So we could ask then to solve the minimization over x and y of our objective function, half x minus 2 squared plus half y minus 4 squared, and then just add some really large constant, we'll call it capital M, times the absolute value of x minus y, right? So M here could be something like 10 to the 25, right? And the answer is, I guess, this can work, right? So this is called a penalty method, where you just add a penalty for violating the constraint. And if you make M big enough, absolutely, the only correct solution will be one in which x is equal to y. So there's two problems with this. One is that you don't know ahead of time how big you have to make M be. So in some sense, the Lagrange multiplier alpha is taking the place of M, and you're solving for how big you have to make M. So that's one problem. The other is there's this nonlinear term, the absolute value of x minus y, and in this simple problem you'd probably be able to figure out what to do with it, but in a more complicated problem, adding this extra nonlinearity could cause trouble in finding the solution. So this is a perfectly valid way to find the solution, with the caveat that you have to guess how big that m is. And the Lagrange multiplier method is basically solving for how big that multiplier has to be. Let's see. Any more questions on Piazza? Looks like, all right, looks like no more questions for now on Piazza. So let's go now back to discrete optimization. So there's a lot of machine learning problems that require optimization over discrete variables, or maybe even harder, over a mixture of continuous and discrete variables. And this, unfortunately, tends to lead to harder optimization problems. However, a lot of the time we can solve them anyway. And so what I'm going to do is I'm going to give some examples of where we might use discrete optimization, and then talk about methods for modeling problems using discrete optimization, like how to set up a given problem as a discrete optimization, and then talk about what kind of software you might use to solve one of these problems. So you guys are probably all playing with outlier detection right now for your assignment. And that's a good example of a discrete optimization problem. It's a discrete decision for each data point whether to call it an outlier or not. Right, and then based on that you would decide, for example, to kick it out of your linear regression fit. Another good example would be a mixture model. So we haven't talked about this before, but let's say, for example, a mixture of Gaussians, right? So what that means is that somebody goes and samples 10 points from a Gaussian distribution, and then they sample 20 points from a different Gaussian distribution, and 30 points from yet a different Gaussian distribution. And then they erase the labels. They hide which distribution each of your points came from, and give you the whole set of 60 points, and ask you to find a model of those 60 points. And so you could find a model by optimizing for each one of the points a guess as to which of the Gaussians it came from, and then you fit a Gaussian to each of those subsets of points. And this is related to the problem of clustering. Each one of these sort of hidden labels tells you which one of the clusters your points belong to, and then it's a Gaussian model within each cluster. Actually, outlier detection is another example of a mixture model. So you could say that I'm fitting a linear regression to the inliers, to the points for which this outlier indicator is 0, and then fit another really simple model to my outliers that, you know, the parameters of that model depend on the outliers, and the parameters of the linear regression are totally unaffected by the outliers. To give maybe a more complicated example, this is an example that comes up all the time. In natural language processing, we might want to parse an English sentence, right? So, you know, if you take an English language sentence like, you know, John saw the man with the telescope. Okay, so your you know, natural language processing system might want to make some kind of a parse of this sentence, right? So, for example, you know, it might want to say that saw is a verb, John is a noun, and John is the subject of the verb, right? And to do this, you would have to disambiguate between at least 2 different possible parse trees, right? So you can see a man who is carrying a telescope, right? That's John saw the man with the telescope, or you could see John could be using a telescope to see a man who's far away, right? And so that's John saw the man, and the seeing is with the telescope, right? So that's two different parse trees. And and of course there's an exponential number of other parse trees that make less sense. For example, you could parse that man is the verb of the sentence and saw is the object of that verb. That would be a bad parse. It would hopefully give a low objective value, but you have to consider that. So so if you want to learn to parse, one way to do this is to try and classify potential edges. So you consider the edge that says from saw to with, right, or that says that basically with modifies saw. That would correspond to the parse where John is looking through a telescope at someone. And you would classify whether that edge is a good edge or a bad edge to include in the parse tree. And you would use features like, what are the identities of the words at each end of the edge? What are the adjacent words? What are the parts of speech, right? You could come up with a lot of different possible features. And then once you've classified for each edge, how well you think it how much you think it seems like a likely edge, you would optimize over the discrete set of possible parse trees to find the parse tree that makes all of your local edge classifiers as happy as possible, that includes as many of the good edges as possible while excluding as many of the bad edges as possible. So that's actually a much more complicated optimization, but we can write it as follows. We would have one binary variable for each edge. The edge is 1 if the variable is 1 if the edge is included in the tree, and it's 0 if the edge is not included in the tree. And then you would include constraints that say that it's a tree. And so one way to include that constraint is to say, well, there have to be exactly n-1 edges total to make a tree over an n-word sentence. And there are no cycles. So any set of edges of which there are n-1 and no cycles forms a tree. And so for the cycles, there would actually be exponentially many constraints. For each set of words, let's say there are k words in your set, you have to not include all of the edges that would make them a cycle, right? So you have to include no more than k-1 edges. And then those are your constraints, and then the score would be the sum over all included edges of how much your classifier likes that edge. So you can see that would be a fairly complicated discrete optimization problem, but it would be one that you would be likely to want to solve as part of a larger machine learning system. All right, so just like with continuous variables, we're going to have to figure out how to model our problem using discrete variables. So I just described, for example, how to go about modeling this parsing problem using discrete variables. And by listening to the description, hopefully it's obvious that this is not necessarily a simple problem to come up with a good description of your problem in terms of discrete variables and constraints. And unfortunately, there's no analog of stochastic gradient descent. So for like almost any continuous optimization problem, stochastic gradient descent may not be the best way to solve it, but it's a halfway reasonable way to solve it. There's not really a corresponding jackknife algorithm for discrete problems. However, if we had to come up with sort of a general tool, it would be the language of mixed integer optimization, and we'll describe that in a sec. So actually, maybe let's describe that now. So in mixed integer optimization, the idea is that you represent all of your variables as either integers or real numbers, and you have equality and inequality constraints that linear equality and inequality constraints that connect them. So, you know, for example, if you wanted to say that, you know, you had the logical constraint that A or B has to be true, right? You would change that into an integer constraint that says that, okay, so here, right, A is either true or false, right? You would change that into, not alpha, but A plus B, right? So here A is in the set 0, 1, same with B, and that has to be greater than or equal to 1, right? And so either A or B has to be 1. It's okay if they both are. It's not okay if both are 0, right? And so you can see that this linear inequality on binary variables, 0, 1 variables, is the same as this logical constraint on true-false variables, right? And so it turns out that you can, we'll talk a little bit more about this later, but it turns out that you can express actually a really wide variety of constraints in this mixed integer optimization language. And then you can use tools that are designed for this language to go ahead and try and solve them. They're not necessarily always effective. You know, it's much easier to come up with an impossible problem than it is for stochastic gradient descent, but you know, nonetheless, there's a lot of useful tools that you can use. All right, so what do these tools look like? So much more so than for continuous optimization. For discrete optimization, it's really important to go find some good tool that somebody has written for you and use that to the greatest extent possible. And the reason is just that it's much more difficult to write good discrete optimizers. People have spent you know, dozens of years working on these things, and you know, at least for the types of problems that they're optimized for, there's just no way that, you know, hand-designed code would be competitive. This is in contrast with stochastic gradient descent, where I would encourage everybody to implement stochastic gradient descent themselves at least once, right? You know, you might actually go and make TensorFlow do the calculations for you if you were doing it in a large-scale system. But what TensorFlow is doing is actually simple enough that you can pretty much understand what's going on, and it's a good idea to understand what's going on under the hood in order to diagnose bugs. That's in sharp contrast to some of these tools that I'll describe later. So some of the useful tools are SAT solvers. So this would be problems with binary variables and constraints of the form A or B or not C. This is, in some sense, the simplest discrete optimization problem. You know, it turns out that, you know, if you look at competition quality SAT solvers, they'll solve actually problems with, you know, millions of variables, even though in the worst case, a million variable SAT problem is essentially impossible to solve. You know, in practice, the ones that you run across are nicer than that, and the competition SAT solvers, they take advantage of some undefinable property of niceness of practical instances in order to be able to solve them much, much faster than the worst case. So as an example of, you know, as an illustration maybe of the fact that these things are ready for prime time, one of the recent FCC Spectrum auctions actually depended on being able to solve SAT problems in the sense that, you know, in the sense that, you know, every loss in solution quality of one of the problems that they had to solve them like, you know, in real time between rounds of bidding, and every time they failed to find the optimal solution, it would cost the FCC millions of dollars. And yet, you know, they were willing to depend on these things, and the auction, by all reports, went off quite well. So There are nice generalizations of satisfiability, SAT, as well. So one of the most common generalizations is max SAT, where instead of the constraints being hard constraints, you have to satisfy all of them. What you would want to do is satisfy as many as possible. Right, so there might be 1 million constraints, and you would like to, you'd prefer to satisfy 900,000 of them instead of 800,000 of them. There are other generalizations of satisfiability as well. SharpSat is a good one. There, instead of just checking whether there's a solution, you want to count solutions. That turns out to be useful for probabilistic modeling. There's also something called SAT modulo theories. So that would be if you wanted to include statements about, for example, integers, you would include a theory of the integers in your SAT problem. And then we get to what's probably the most general purpose tool, which is a mixed integer solver. So good commercial examples of these are Cplex and Gurobi. These handle, as I said before, arbitrary, binary or categorical or role-valued variables. They handle arbitrary linear constraints on these variables, which are pretty powerful, as we'll see in a sec. And unfortunately, they are incredibly expensive. CMU has site licenses to tools like these, so you can use them for free. But if you were in a, company, you would expect to pay $10,000 per seat to use one of these things. But that doesn't mean, you should take advantage of being a student and use these things while you can. All right. So let's talk now about how to model different kinds of constraints. One of the most common constraints is a logical formula. For example, if we set all of A, B, and C to be true, then we must set D to be false. That would be a logical constraint. So SAT is an example where all of the constraints are logical formulas of a particular form. They're disjunctions of variables or negated variables. You could imagine taking this, parsing problem and writing it in terms of logical constraints. For example, if you interpret a particular word as a verb, then it must have a subject, right? Or if you interpret it as a noun, it cannot have a subject. And so any logical constraint you can represent in a mixed integer program, meaning that you can set true to be 1, false to be 0, and represent your logical constraint in terms of inequalities. And to show how that works, I'll work through an example. There's some questions up here on Piazza. Oh yeah, so somebody is asking, how can a SAT solver work given that SAT is NP complete? Excellent question. And in fact, mixed integer programming is, at a minimum NP complete. It's, it's no easier than NP complete. So all of these problems are NP hard, meaning no easier than NP complete. So that means that worst case, they take exponential time. So this is what I meant by saying before that in the worst case, you just cannot solve these problems. If you have a worst case SAT problem with 1 million variables, you're just sunk. There's just no way that you will ever discover the solution to it. However, in practice, when you take problems that you actually care to solve and model them as SAT problems or as mixed integer programs, these problems are easier in some undefinable way than the worst case. And so these solver systems that you can buy, they've been engineered over decades to take advantage of whatever this property of being a real-world problem is, like whatever kinds of niceness are common in real-world problems. And in practice, they actually, they're kind of finicky, right? Like it's really easy to accidentally create a problem that these things can't solve. But with some practice, you can also create problems that are quite large that they're able to solve quite effectively. And so that was the example that I gave about the FCC auction. You know, in the worst case, they could have run across a SAT problem that they had to solve that was just impossible to solve, and then they would have lost money because of that. And they were willing to trust that they would be able to solve all of the problems that they ran across, and it turned out that they were justified in this trust because the auction went well and earned them a bunch of money. All right, so so going back to how to model logical constraints. So I already gave this example that a plus b bigger than or equal to 1 is equivalent to a or b. And another maybe slightly more complicated example is a k of n constraint, right? If you, the constraint that a plus b plus c plus so forth, right, a list of n variables is bigger than or equal to k, says that you have to set at least k of those variables to be true. And so and is an n of n constraint, and or is a 1 of n constraint, and there's a whole bunch of different k of n constraints in between. But you can take actually pretty much any logical formula and recursively translate it to a set of linear inequalities. And so I've given rules for doing so here, but maybe it's it makes more sense to do an example, right, to show how these rules work. So for our example, we're going to start from this formula here, right? A or not B or C and B or D, whole thing negated, right? So the first step is to push all of the negations. So what I'm going to do, I'm going to show a procedure that will work for any formula that contains and, or, and not as its connectives. And that's a fully general set of connectives. You can express any logical constraint in terms of those connectives. And so what I'm going to give is a general procedure for representing logical formulas as inequality constraints. So the first step here is to use De Morgan's laws to push all of the negations inward, right? So De Morgan's laws say that if you have a negation of an and, that's equivalent to pushing the negation through, negating each of the individual variables, and flipping the and to an or. And then vice versa, if you start with an or, when you negate it, it flips to an and. So if you start from this expression, right, you push the negation through this and, you flip the and to an or, and you have a negation of both of the arguments of the or. And then recursively, you push this negation through the or, flip it to an and, right? And same thing, you push this negation through the or, flip it to an and. And I use double negation elimination, so you negate not B, and you turn that into B, right? So then what you do is you build a parse tree for your formula. So a parse tree looks like this. It's basically, you take this formula, you have an or at the top of the parse tree. Its two children are these two formulas here, both of which are ands, right? The first formula has children not A, B, and not C. And the second formula has children not B and, excuse me, not D. All right, so here's the parse tree for this formula. And what we'll do is from the bottom of the parse tree going up, we'll, for every internal node, create a new variable and a constraint to evaluate it. So we'll label these nodes. Let's call them R, S, and T, right? And so this is, each of these is a new binary variable. And so let's look at S first. So for S, what will happen is that we know that we want S to be the and of not A, B, and not C. So we'll say that let's see, so we'll say that 3S has to be less than or equal to not A, which is 1 minus A plus B plus 1 minus C, right? So what this says is that if A is false and B is true and C is false, this right-hand side evaluates to 3. So S can be either 0 or 1, right? Because 0 is less than or equal to 3 and 3 is less than or equal to 3. If this formula isn't satisfied, right, then the right-hand side is less than 3 and so S can only be 0. Okay? Same thing for T. So 2T is bigger than, less than or equal to 1 minus B plus 1 minus D, right? And here, right, the coefficient of T is the count of the number of terms on the right-hand side. Same thing with the coefficient of S there, right? And then R is the root, and so we'll have a constraint that says that R is less than or equal to S plus T. And so since this is an OR constraint, we just say that R instead of 2R is less than or equal to S plus T. That says that if either S is 1 or T is 1, then R can be 1. If they're both 0, then R has to be 0. Right? And now we're at the root, and so we add one last constraint, which is that the root node has to be bigger than or equal to 1. Right? Which is to say it has to equal 1. And so in order for the root node to be bigger than or equal to 1, well, that means that either S or T has to be true, right? And so if S is true, that enforces this constraint, right? It says that 3 is less than or equal to that, which means that all of these guys have to be true here. Or if T is 1, that means that 2 is less than or equal to the right-hand side of the inequality, which forces both of these terms to be true, right? So you can see how that works, right? So we push all of the negations to the leaves, we build a parse tree, and we push all of the negations inward using De Morgan's laws. We build a parse tree like this, we add a new binary variable for every internal node of the parse tree, and we create constraints that implement the ands and the ors, and then finally we say that the root node has to be 1. And that's how we change a logical constraint into a set of inequalities on binary variables. Okay, so just if you, to pop up, the reason that we were doing this is as part of showing how to model a problem using a mixed integer program, right? So we might have started off with a logical expression of our constraint, but if we want to use a mixed integer program, we have to write that logical constraint in terms of binary 0, 1 variables and linear inequalities and equalities. Okay, and so this shows how to do that. All right. So another example of how to do modeling in a mixed integer program, a task that we often need to do is to connect our binary variables to our continuous variables. For example, we might want our continuous variable x to be 0 if our discrete variable z is 0, but we might want x to be just non-negative if z is 1. And so we can enforce that using what's called the big M trick, or the big M idiom, which is we always enforce x is bigger than or equal to 0, because that's true in either of the cases. Z is going to be our binary variable, and x has to be less than big M times z. And big M here is a very large constant, chosen so that we know a priori that x can't be any larger than m. So this is actually kind of similar to the question that somebody asked on Piazza earlier in the lecture, except here, there's, in the Lagrange multiplier example, there was an easier way to solve the problem than to include this big M. Here, the big M is probably the best way to solve the problem, right? So if z is 1, then this constraint is just that x is less than or equal to m, which is no constraint at all, because we know that ahead of time. And if z is equal to 0, then x is less than or equal to 0. And since x was also bigger than or equal to 0, we've enforced that x has to equal 0. Okay. And so you can use big M to also enforce more complicated constraints. The rest of the section describes how to do it. I'm not going to spend a lot of detail on interpreting that. All right. So so once we've gone and we've modeled our problem as a mixed integer program, or any other form, we have to go and use some algorithm to try to solve it. And I guess the first thing is that, well, okay, we just, import the problem into an implex of Gurobi and set it loose and have it give us the answer, right? And so in many cases, that's all you need to do. However, it makes sense to know a little bit about the algorithms that are going on inside Gurobi or related software so that you can diagnose things that are going wrong, or so that you can maybe solve part of the problem in an outer loop and just give smaller problems to Gurobi. And so you would do that like if you know something about the structure of the problem that lets you write a good outer loop, better than what Gurobi would have created by itself. All right. So one of the simplest algorithms is hill climbing. Hill climbing means that we randomly initialize our variables and then repeatedly take a single variable or a small group of variables and try to improve our objective according to them by adjusting just those variables. And so our objective will keep going up and up, and at some point it plateaus, and so we've at that point gotten to a local optimum, and so we randomly reinitialize and hill climb again from our new point. And so we want lots of restarts and run hill climbing for a while from each one of these restarts, and then the best solution we've seen across all of these restarts is the solution that we return. So hill climbing is not necessarily a fancy algorithm, but it's really easy to implement. And each iteration of hill climbing can potentially be quite fast, so it's a decent choice to do for many problems. A variant of hill climbing is coordinate ascent, where, so in hill climbing we just try to improve, like maybe take a, like flip a variable in the direction that improves the objective or something like that. Coordinate ascent means to specifically optimize over a single variable or a small subset of variables. In particular, let's say you had a continuous variable, hill climbing might be you would take a gradient step to try and improve things, whereas coordinate ascent would be you solve for the optimum with respect to that variable. Either hill climbing or coordinate ascent can be better. It depends, for example, on how easy it is to optimize with respect to a single variable while you hold all of the other variables fixed. If you're doing it with respect to multiple variables at once, it's called block hill climbing or block coordinate ascent. Lasso is an interesting problem in the sense that we've written it as a continuous problem, but in fact we are making a discrete decision about whether to set each coordinate of our weight vector to 0. And so hill climbing is actually a pretty decent algorithm for lasso. In fact, specifically coordinate ascent turns out to be a very good algorithm for lasso in large-scale problems. And so the way that would work is that you repeatedly pick a component of your weight vector and you optimize your objective function with respect to that component. So your objective function has a quadratic term and then an absolute value term. And so you would have a one-dimensional, when you specify to a single component of your weight vector, you'd have a one-dimensional quadratic and an absolute value term. Turns out that you can effectively check all three ranges of the absolute value, right? You just check whether a negative solution is true, you check whether 0 is optimal, and you check whether a positive solution is optimal by computing, setting the derivative to 0 under each of those assumptions. So it's fast to solve a problem like this, and so hill climbing and in particular coordinate ascent can have very fast iterations for lasso. Another good example of this one's of block coordinate ascent, which is the clustering problem I mentioned. So in the mixture of Gaussians model, or more generally just in a clustering problem where you want spherical clusters. We have a question about coordinate ascent. So somebody wants to know whether you could do coordinate ascent. So I defined coordinate ascent as going to the global maximum of a particular variable with while holding all of the others fixed. You could also define a version of coordinate ascent where you go to the local maximum of a given variable while holding all of the other ones fixed. Either one of those could be a perfectly good algorithm. Coordinate ascent works best for problems where you can actually compute the global maximum with respect to a single variable efficiently, as is the case in lasso, for example. And so, that's maybe a best case for implementing coordinate ascent. But, going to a local maximum with respect to a given variable, that's just another example of hill climbing, and it could be a very good algorithm depending on the details of your problem. Let's see. So right. So here is a clustering objective. So we have a whole bunch of indicator variables, Zij, which is 1 if xi is assigned to cluster J, and 0 otherwise. And so this objective, right, there's going to be, for each I, there's going to be exactly one of these terms that's non-zero, the one corresponding to the cluster that's assigned. And so you want each point to be as close as possible to its corresponding cluster center. Right, so that's a nice mixed integer program. And you could directly hand that mixed integer program to Cplex or Gurobi, and in fact, with a little bit of massaging, you can get that problem into a form that Cplex and Gurobi can solve quite quickly sometimes. But a simpler algorithm would be block coordinate ascent, which is to say you hold, so your variables are the z's and the mu's, x's are your problem data, and so you could hold all of the z's fixed and optimize with respect to the mu's, and that means that you would set each one of the mu's to be the average of all of the xi that are assigned to that center. And then you hold the mu's fixed and you optimize with respect to the z's, and that means just to assign each x to its closest cluster center. And so that's a good example of a block coordinate ascent algorithm that works quite well in practice. That algorithm is called the k-means clustering algorithm. And it tends to converge pretty rapidly to a pretty good local optimum. You can even give performance guarantees if you initialize appropriately, which is kind of cool. All right, you can make a stochastic version of hill climbing, which is that instead of optimizing with respect to a given group of variables, you just simply randomly perturb it. And if things get better, you keep the perturbation. And if things don't get better, you throw away the perturbation and keep the original values of the variables. And then you pick another set of variables, perturb them, and keep on going. So stochastic hill climbing, each individual step makes potentially less progress than coordinate ascent, for example, but each individual step can be much faster, right? Like randomly perturbing is a pretty simple operation compared to optimizing. The other nice thing is that the extra randomness can help kick you out of local optima. And so stochastic hill climbing could get to a better optimum, better local optimum given a particular initialization point. All right. So let's see. So yeah. All right. So I want to make sure that I have time to answer questions about any topics that people are still confused about before the exam. So what I'm going to suggest doing, I'm going to keep going over these last few blocks of the lecture notes, but if you I'll keep an eye on Piazza, and so if you want to ask questions about just any topic that's confusing you, please go ahead and ask them. I'll prefer to answer those instead of spending all of the rest of the time on the last few blocks of the notes. So somebody's asking about step size in stochastic hill climbing. So I didn't actually define a step size in stochastic hill climbing, but there's a common variant of stochastic hill climbing where, for example, if you have a bunch of Gaussian variables, a bunch of continuous variables, you would add a Gaussian perturbation to them, and then the width of that Gaussian would be analogous to a step size. And so you would then trade off. If you take a really large step size, you would tend to make rapid progress. You'd move your iterates a lot on each iteration. But if you're at a good point and you perturb it by a lot, well, a lot of times it'll get worse. And so you might accept fewer of your perturbations, and that would slow down your progress. And so there's a trade-off in that step size. And so the question was about how the step sizes compare between stochastic hill climbing and ordinary hill climbing, by which I guess we're thinking of gradient ascent. I should point out, by the way, that hill climbing does not equal gradient ascent, right? Like, one way to perturb your variables to improve them, if they happen to be continuous, is to take a step along the gradient. But that's not the only way to perturb your variables to improve them, and it doesn't even work if your variables are discrete. So hill climbing is more general than gradient ascent. But so the question is about the relative step sizes in hill climbing versus in deterministic versus stochastic hill climbing. I don't think that there's necessarily anything you can say in general about that. In both cases, there's a trade-off, right? If you take too big a step, you might actually decrease your variables, but if you take too small a step, you're never going to get anywhere. All right. So all right, so yeah, put questions up on Piazza. So far I don't see any conceptual questions on Piazza. So let's talk about probabilistic inference. So one of the ways that a discrete optimization problem often arises is a probabilistic inference question, which means that you start with a probability distribution over a lot of variables. Some of those variables could be discrete, other ones could be continuous. We observe some subset of the variables. Let's say C for conditioning to indicate the indices of the variables we observe. We want to marginalize out some of the other variables, so we don't care about their values. We just want to get rid of them. And O for the variables that we want to optimize. So M is going to be the subset that we want to marginalize, and O is going to be the subset we want to optimize. And so then what we want to solve is this problem. We have the probability So this is the conditional probability of xo and xm given xc. If we sum out xm, we get the marginal of xo given xc. And then we want to maximize the probability. We want to pick the assignment that maximizes probability. And so this is a type of probabilistic inference problem that comes up fairly often. An example would be a Gaussian mixture model, which is the probabilistic version of k-means clustering. So in a Gaussian mixture model, we would say that there's a categorical random variable that says which cluster center a given point is assigned to, and then a Gaussian random variable that says what's the distance from your cluster center. And we don't observe either of those. And so what we would like to do is marginalize out the cluster assignments and the distance from the cluster center, and then optimize over the cluster centers. Find the cluster centers that make the data as likely as possible. And so you could write that as a problem of this form here, where the thing you condition on are your data, the stuff you marginalize out are the cluster assignments and the are the cluster assignments, and the thing you optimize over the cluster assignments and I guess the error, and the thing you optimize over is the cluster center locations. And so if you write that out, you'll get an objective that looks like this. This is the log probability. And so if this should look familiar. This is just the k-means objective, and in fact if we optimize over z and mu, we get back k-means. But in this, what we want to do is marginalize over z, right? So we want to take the version of this, we want to marginalize the probability over z, which is going to wind up getting us a sort of a more difficult optimization problem. Missing data is maybe another good example of a probabilistic inference problem. We'd like to marginalize out the possible values of the missing data. And so to solve problems like this, these are actually, these go beyond what you can easily solve using a mixed integer program. And so we need sort of more sophisticated, or at least more expressive algorithms to handle them. And Gibbs sampling is a good example of such an algorithm. All right. So so what I was going to do, the last thing to discuss is how the Gibbs sampling algorithm works. So in Gibbs sampling, let's start from, all right, we've got some, all right, still no conceptual questions on Piazza, so let's describe the Gibbs sampling algorithm. So Gibbs sampling is kind of like hill climbing. That's actually why I included it as an algorithm here, because conceptually it's a fairly straightforward algorithm. It's like the sort of immediate generalization of hill climbing to this more to this richer setting. So let's start by with Gibbs sampling with no variable to optimize over. So every variable is either marginalized or conditioned. Obviously, later we're going to want to add back in the optimization, but for now let's look at this. So what we're going to do then is repeatedly pick a single variable or a small subset of variables from the ones we're marginalizing, and set it to be, instead of optimizing over it, we're going to figure out its conditional distribution given all of the other variables, so all of the variables in XC and all of the variables outside our block in XM. and we figure out the conditional distribution over our current block of variables, and we sample from that conditional distribution and set the variables to be that sample. So, here's an example. In the Gaussian mixture model, you can derive the conditional probability of all of our cluster assignments given the means. It's, a probability, basically closer centers are more probable with an e to the minus x squared fall off as you get farther away. And then the conditional distribution of the mean is basically a Gaussian whose center is the average of all of the points that are assigned to that cluster, and the variance depends on how many points are assigned to that cluster. And so you can fix all of the means and sample all of the conditional distributions independently. Sorry, all of the cluster assignments independently. And then the same thing, you can fix all of the cluster assignments and sample all of the means independently. And so that would be block Gibbs sampling. And in general, you just keep doing this for a long time. And unlike hill climbing, it's difficult to tell when to stop, right? So in hill climbing, things get better and better and better, and then they tail off. Here, because we're randomizing, things could get better and then worse and then better and then worse. And so what's going to happen is you initialize somewhere that's not high probability in your distribution. And so, you look at the probability of that and it's going to be low, it'll get higher and higher and higher, and then it'll like bounce around. And it's bouncing around within some sort of, band of relatively high probability points. And so that's sort of the diagnostic for convergence of Gibbs sampling, that you're at least sort of a local optimum, so to speak. It's not quite the same as a local optimum when the probability of your points, it's still bouncing around, but it's not getting any higher. All right, so that's Gibbs sampling. So Gibbs sampling is a special case of a more general method called Metropolis-Hastings, and Metropolis-Hastings is a special case of a more general class of algorithms called Markov chain Monte Carlo. Again, you can take entire courses on all of these algorithms, and I recommend doing so. They're interesting to learn about. But I wanted to give at least one algorithm from this class in order to get a flavor of the sort of thing that we might use. Gibbs sampling has a nice guarantee, which is that if you run it for long enough, and you pick a random iteration, and you look at the value of your variables in M, it will be approximately a sample from the true conditional distribution of those variables given the stuff you're conditioning on. So that's a nice guarantee. Unfortunately, we don't know how long we have to wait. And so there's like a whole cottage industry of convergence diagnostics for Gibbs samplers to tell when it's safe to say, okay, we've converged, we can take a sample now. All right. And so the last thing that I wanted to talk about now was to add back in the variables that we're optimizing over. And so Gibbs sampling will not quite give us the answer we want to have. It would let us, for example, sample from this conditional distribution, the distribution of over both XO and XM given XC. But if we want to optimize as well, we can collect a whole bunch of samples. Like, we run our Gibbs sampler, let it converge for, let it run long enough to converge, and take some samples of XO and XM. We throw away the XOs, and we take XM as a sample of the marginal distribution of XM given XC. And then probability of XO given XC is approximately equal to the average over all of our samples of M of the probability of XO and XM given XC. right? So this then becomes an objective that we can optimize using ordinary hill climbing. So so just to recap, we have this this more complicated problem here. We solve it in 2 steps. We use Gibbs sampling to get a sample of the marginal distribution of xm given xc. Then we average, we construct an estimate of our objective for xo using that sample over xm. And we optimize that using plain old hill climbing, as we described before. So I think this is a good place to stop. My office hours start now. Keep asking questions on Piazza, and good luck on the exam on Wednesday. And yeah, and I hope you enjoyed the course. I'll talk to you guys later.